Every image of a black hole you have ever seen contains an assumption, a quiet assumption, a reasonable assumption, the kind of assumption human beings make automatically whenever they look at a picture. The assumption is that the thing in the image is the thing itself, that when we see a glowing ring surrounding a dark center, we are looking at an object, a place, a destination, something that exists in the same way that a mountain exists, or a planet exists, or a star exists. But the reality may be stranger, because the dark center in those famous images is not actually the black hole. It is the absence left behind by something we cannot see, something that, by definition, refuses observation, something whose true nature may remain permanently hidden behind the limits of physics itself. And this is where the discomfort begins, not with what black holes are, but with the possibility that we do not really know. For more than a century, black holes have occupied a strange place in human thought. They are among the most famous objects in science. Children learn their names. Films build stories around them. Artists paint them. Writers imagine journeys into them. Entire generations have grown up believing that black holes are one of the great discoveries of modern astronomy. A solved mystery, a completed chapter. Yet beneath this familiarity lies an uncomfortable fact. No human being has ever directly observed a black hole. No telescope has ever captured one. No spacecraft has approached one. No instrument has measured what truly exists beyond the boundary we call the event horizon. Everything we know comes indirectly. From shadows, from motion, from light bending around invisible structures, from mathematical descriptions that seem astonishingly successful and yet remain incomplete. The black hole, despite its fame, remains hidden, and hidden things have a way of becoming stranger the longer they survive examination. At first glance, the modern picture appears reassuring. Massive stars die, gravity overwhelms, matter collapses inward, space and time curve so severely that escape becomes impossible. An event horizon forms, a black hole is born. The story sounds clean, elegant, finished. But science has a history of becoming most interesting precisely when stories appear finished, because reality rarely rewards certainty. Again and again, throughout the history of astronomy, the universe has revealed itself to be larger than expected, older than expected, more complicated than expected. Humanity once believed Earth occupied the center of existence. Then we learned it did not. We believed the sun occupied a privileged position. It did not. We believed our galaxy might contain the entire cosmos. It did not. Each discovery expanded reality outward. Each correction made the humanity smaller, and each time the universe became harder to intuit. Black holes seem poised to continue that tradition. The more closely physicists examine them, the less secure the foundations begin to feel. Equations that work perfectly elsewhere start producing contradictions. Concepts that normally coexist begin fighting one another. The deepest theories in modern science suddenly refuse to cooperate. General relativity, humanity's greatest description of gravity, predicts black holes naturally. Quantum mechanics, humanity's most successful description of the microscopic world, predicts something else. Both theories work extraordinarily well. Both have survived every experimental challenge. Yet inside a black hole, they appear incapable of agreeing on reality. Somewhere beyond the horizon, our understanding breaks. And when understanding breaks, uncertainty rushes in. Imagine standing on a shoreline at night. The ocean stretches beyond sight. The surface appears calm. You know something vast exists beyond the darkness. Something real. Something physical. Yet your eyes cannot reach it. Your mind fills the gap with assumptions. You imagine shapes, distances, boundaries, series. But imagination is not observation, and certainty is not knowledge. Black holes occupy a similar position within science. They sit beyond a horizon not merely of distance, but of comprehension. We know they exist. The evidence is overwhelming, yet the deeper question remains strangely unsettled. What exactly exists there? What is a black hole fundamentally? A region of space, a collapsed star, a defect in space-time, a quantum object, an illusion produced by incomplete mathematics, or something even stranger that current language cannot properly describe? The unsettling possibility is that black holes are not mysterious because they are distant. They are mysterious because they may expose limits within human understanding itself. Limits hidden for centuries. Limits we only discovered because nature accidentally built laboratories larger than galaxies and more extreme than anything we could ever construct. In that sense, black holes are not merely astronomical objects. They are tests, experiments conducted by the universe, places where reality pushes its own rules to the breaking point. And what those experiments reveal may be far less comforting than the simple diagrams found in textbooks. Because if black holes truly expose flaws in our understanding of space, time, matter, information, and causality, then the darkness at their centers is not the most important mystery. The most important mystery is why the universe allows such contradictions to exist at all, and whether the black hole itself is only the shadow cast by a deeper reality we have not yet learned how to see. For most of human history, the universe felt understandable. Not simple, perhaps not small, but understandable. The stars moved across the sky in predictable patterns. The sun rose and where? The moon changed shape. Seasons arrived and departed. Storms came and went. The cosmos appeared orderly. Even when ancient civilizations filled the heavens with gods, spirits, and myths, they still imagined a universe that operated according to familiar principles. The sky might be divine, but it was not fundamentally alien. The same intuition survives today. Modern science has replaced mythology with mathematics, but deep beneath our knowledge, the human brain continues to interpret reality through assumptions shaped by everyday experience. We expect causes to precede effects. We expect objects to occupy places. We expect time to move forward. We expect information to persist. We expect space to be a stage upon which events occur. These assumptions feel so obvious that questioning them seems unnecessary. And for almost everything in ordinary life, they work remarkably well. A falling apple follows predictable rules. A planet orbits a star. A spacecraft crosses the solar system. The equations may become complicated, but the underlying picture remains recognizable. Reality appears structured, stable, coherent. The universe feels like a place. Black holes become unsettling because they begin by fitting comfortably inside this familiar worldview. At first, they seem almost intuitive. Imagine a star far larger than the Sun. For millions of years, nuclear fusion pushes outward against gravity's relentless pull inward. The star survives because these forces remain balanced. Gravity tries to crush. Fusion tries to resist. A temporary truce is established. But stars are living on borrowed time. Every second, unimaginable quantities of fuel vanish within their cores. The process is slow by human standards and astonishingly fast by cosmic ones. Eventually the fuel runs out. The outward pressure weakens. Gravity wins. The star collapses. This story feels understandable. It resembles countless events we witness every day. Structures fail when support disappears. Buildings collapse when foundations weaken. A bridge falls when enough material is removed. A dying star seems merely a larger version of the same principle. And this intuition helped scientists accept black holes when the idea first emerged. The basic logic felt elegant. Mass creates gravity. Enough mass creates stronger gravity. Enough gravity causes collapse. Enough collapse creates a black hole. Problem solved. Except reality rarely remains that cooperative. The first hints appeared long before anyone used the term black hole. In the 18th century, the English natural philosopher John Michell considered a strange possibility. What if a star became so massive that even light could not escape? At the time, light was often imagined as a stream of particles. If gravity pulled strongly enough, perhaps those particles would fall back. The idea was extraordinary, yet it remained largely philosophical. There was no evidence, no observational path, no reason to believe such objects truly existed. For generations, the concept drifted quietly through scientific history. Then something remarkable happened. Humanity discovered that gravity itself was not what it seemed. In 1915, Albert Einstein published general relativity. The theory transformed gravity from a force into geometry. Space and time were no longer separate backgrounds. They became participants. Matter told space-time how to curve. Space-time told matter how to move. The familiar universe suddenly became stranger than anyone had imagined. Planets were not being pulled through space. They were following curves within space-time itself. Gravity was no longer an invisible force reaching across emptiness. Gravity was the shape of reality. This realization represented one of the greatest intellectual achievements in human history. Yet hidden inside Einstein's equations was something deeply troubling. Under extreme conditions, space-time appeared capable of collapsing, not metaphorically, literally. A few months after Einstein published his theory, German physicist Karl Schwarzschild discovered an exact mathematical solution. The equation suggested that if enough mass occupied a sufficiently small region, space-time would curve without limit. A boundary would form. Beyond that boundary, every possible future pointed inward. Escape would become impossible. The mathematics described something that sounded absurd. Even Einstein found aspects of the implication difficult to accept. Many physicists assumed nature would prevent such objects from forming. Surely some unknown process would intervene. Surely reality would avoid such This expectation was understandable. Science often encounters mathematical possibilities that never appear in nature. Equations can describe many things that do not exist. Perhaps black holes belong to that category. For decades, uncertainty remained. Then the universe began providing evidence. Stars exploded. Galaxies behaved strangely. Invisible masses influenced visible matter. The cosmos repeatedly hinted that something enormous and unseen lurked in the darkness. Gradually, black holes transitioned from theoretical curiosities into physical objects. Yet something important happened during that transition. Humanity unconsciously simplified the concept. The public imagination transformed black holes into cosmic vacuum cleaners, monsters drifting through space, hungry objects consuming everything nearby. The image became culturally powerful. It also became misleading, because black holes do not behave like cosmic predators. If the sun were magically replaced by a black hole of identical mass, Earth would continue orbiting almost exactly as before. The seasons would just disappear because sunlight would vanish. The world would freeze, life would die. But our orbit would remain largely unchanged. Gravity at Earth's distance would be nearly identical. This fact surprises many people because it conflicts with intuition. We imagine black holes as possessing supernatural gravity. In reality, their most unusual properties emerge not from strength alone, but from concentration. The mass is compressed. The geometry changes. The structure of space-time becomes extreme. And this distinction matters because it reveals a deeper lesson. The universe is often stranger than the metaphors we use to understand it. Every simplification introduces distortion. Every mental image sacrifices accuracy. Every familiar explanation conceals hidden complexity. For a long time, that complexity seemed manageable. Scientists believed black holes were unusual but ultimately understandable consequences of known physics. Exotic, yes. Mysterious, certainly. But not fundamentally threatening to our picture of reality. Then the questions became deeper. The observations became sharper. The mathematics became more precise. And slowly a disturbing realization emerged. The challenge posed by black holes was never their existence. The challenge was what they implied, because the closer physicists looked, the more they discovered that black holes were not merely objects within the universe. They were places where our most trusted descriptions of reality began colliding with one another. Places where certainty weakened. Places where understanding fractured. Places where the universe seemed to whisper that the story humanity had assembled carefully, brilliantly, over centuries might still be incomplete. And if the story remains incomplete, then the darkness surrounding black holes is not merely physical darkness. It is intellectual darkness, a region where knowledge itself begins to fade, a horizon beyond which even our best ideas struggle to survive. The first truly unsettling thing about black holes is that humanity discovered them without ever seeing them. Not because our telescopes were too weak, Not because they were too far away, but because black holes are fundamentally different from almost every other object astronomy has ever studied. Astronomy is usually the science of light. For thousands of years, every major discovery began with something visible. A brighter star, a wandering planet, a comet crossing the sky, a distant galaxy. Even modern instruments remain, in essence, sophisticated methods of collecting light. Radio waves, infrared radiation, X-rays, gamma rays, visible photons, these are all different forms of the same cosmic messenger. The universe tells its story through light. Black holes do not, at least not directly, and this creates a peculiar situation. Imagine trying to understand the existence of an animal that leaves no footprints, casts no shadow, produces no sound, and cannot be observed under any circumstances. The only evidence would come from its influence on other things. Branches moving unexpectedly, disturbed water, sudden absences, a pattern of effects suggesting an invisible cause. This is remarkably similar to how black holes entered modern astronomy. They announced themselves indirectly, by disturbing their surroundings, by changing the behavior of nearby matter, by revealing the presence of something hidden. And hidden things are often more psychologically unsettling than visible ones, because visibility provides boundaries. When we can see something, we can estimate its size, its distance, its shape, its location. We can place it comfortably within a mental framework. But invisible objects resist those instincts. They remain undefined, partially imagined, always slightly beyond certainty. For much of the 20th century, black holes occupied exactly that position. Scientists found stars orbiting unseen companions, gas clouds accelerating towards invisible masses, rays emerging from regions where no visible source existed. Again and again, observations pointed toward objects possessing enormous gravity and astonishing density. The evidence accumulated slowly, not through a single discoverer, not through a dramatic revelation, but through decades of increasingly persuasive clues. One of the most important lessons of science is that certainty rarely arrives all at once. Reality reveals itself gradually. Each observation contributes a fragment. Each fragment modifies the picture, and sometimes the final image becomes stranger than anyone anticipated. By the late 20th century, astronomers had become increasingly confident that black holes were real. Yet confidence created an unexpected problem. The more evidence accumulated, the more black holes began appearing everywhere. Not literally everywhere, but in places where nobody expected them. Massive stars seemed capable of producing them. Binary systems contained them. Dense stellar environments hosted them. Then an even more surprising discovery emerged. Galaxies themselves appeared connected to black holes. At first this sounded absurd. Galaxies are immense. Black holes are comparatively tiny. Even the largest known black holes occupy only a minute fraction of the volume of their host galaxies. The relationship seemed impossible, and yet observation after observation pointed toward the same conclusion. Near the centers of galaxies lurked invisible giants, not merely stellar remnants, something far larger, something millions or billions of times more massive than the Sun. Today, astronomers believe that most large galaxies contain a supermassive black hole at their core, including our own. The realization is difficult to absorb emotionally. Human beings naturally think in scales that fit within experience. Cities, countries, continents, even planets stretch intuition. Galaxies already exceed ordinary comprehension. The Milky Way contains hundreds of billions of stars spread across distances so enormous that light requires roughly 100,000 years to cross it. A human civilization could rise, flourish, collapse, and vanish many times before a single photon travelled from one side to the other. Yet at the centre of this immense structure sits something invisible, something whose gravity controls the motion of nearby stars. Something that may contain millions of solar masses compressed into a region smaller than our solar system. The black hole at the heart of the Milky Way is known as Sagittarius, a star. For decades it remained little more than a suspicion. Astronomers could not see it directly. Instead, they watched stars orbiting apparently empty space. Year after year, decade after decade, the stars moved exactly as gravity predicted. They accelerated near a central point. They traced invisible paths around something hidden. The evidence became overwhelming. There was no visible object large enough to explain the motion. Only an unseen concentration of mass. Only a black hole fit the observations. This achievement represented one of humanity's most extraordinary intellectual victories. Scientists inferred the existence of an invisible object 26,000 light-years away by measuring tiny motions across the sky. The accomplishment was breathtaking, yet it also carried a deeper implication. The center of our galaxy is not what it appears to be. The calm band of stars stretching across the night sky conceals something fundamentally inaccessible, a gravitational abyss around which entire stellar populations move. And suddenly the familiar universe becomes less familiar. The Milky Way no longer feels like a collection of stars. It begins to resemble a structure organized around an invisible center, a hidden engine, a darkness embedded within light. This pattern repeats across the cosmos. Again and again, black holes appear not as rare exceptions, but as central participants in cosmic evolution. Some actively consume surrounding matter. Others remain relatively quiet. Some produce jets extending thousands of light-years into intergalactic space. Others hide almost completely. But nearly all challenge a basic human expectation. We assume important things should be visible. Reality disagrees. The universe repeatedly demonstrates that its most influential structures are often hidden. Dark matter cannot be directly viewed. Dark energy remains mysterious. Black holes refuse direct inspection. The visible universe may represent only a small fraction of what actually exists. And this realization slowly changes the emotional character of astronomy. Early astronomy expanded humanity's horizon. We discovered new worlds, new stars, new galaxies. Reality grew larger. Modern astronomy does something more unsettling. It reveals how much remains unseen. The expansion is no longer merely outward. It is inward, into ignorance, into uncertainty, into the recognition that observation itself may be limited. Black holes occupy a special place within this transformation because they force us to confront a profound asymmetry. We know they exist. We can measure their effects. We can calculate their properties. We can even predict their behavior with astonishing precision. Yet the object itself remains hidden. The center remains concealed. The essential reality remains inaccessible. And this raises an uncomfortable question. What if our confidence exceeds our understanding? Science is extraordinarily powerful. It has mapped galaxies, decoded atoms, detected gravitational waves, and reconstructed the history of the universe. Yet black holes continually remind us that explanation is not the same thing as comprehension. Knowing how something behaves does not necessarily mean knowing what it is. A clock may reveal time without explaining its origin. A map may reveal geography without revealing meaning. A set of equations may predict phenomena without describing their ultimate nature. Black holes increasingly occupy this strange territory. We can describe them, model them, measure them, even photograph their shadows. But the closer we approach the core question, what is actually there, the less certain the answers become. And this is where the first layer of confidence begins to crack. Because the scientific story initially appears straightforward, an invisible object reveals itself through gravity. Evidence accumulates, the case becomes stronger, the mystery shrinks. That is how discovery is supposed to work. Yet with black holes, the opposite often occurs. Each answer creates deeper question. Each observation exposes new uncertainties. Each improvement in understanding reveals larger gaps beyond it. The invisible object at the center remains hidden, not merely because it is distant, but because reality itself seems to place a boundary around it, a boundary that observation cannot cross, a boundary that mathematics can approach but not fully explain. And as scientists pushed closer to that boundary, they discovered something unexpected. The greatest challenge was not finding black holes. The greatest challenge was understanding what exactly we had found. The photograph seemed to settle everything. For decades, black holes had existed primarily as mathematical predictions and indirect observations. Astronomers measured stars orbiting invisible masses. They detected violent bursts of radiation from regions where no visible object could be found. They watched entire galaxies behave as though immense hidden structures occupied their centers. The evidence was overwhelming, yet there remained a psychological gap. Human beings trust images. We always have. An equation may persuade the intellect, but a picture persuades something deeper. Pictures feel immediate, concrete, final. So when the first image of a black hole was released in 2019, many people experienced the moment as a conclusion. The mystery, it seemed, had finally become visible. At the center of the image sat a dark circular region surrounded by a glowing ring of hot gas. Newspapers around the world published it. Television broadcasts celebrated it. The image rapidly became one of the most recognizable scientific achievements of the century. The object photographed was the supermassive black hole at the center of the galaxy Messier 87. Its mass exceeded 6 billion suns. Its event horizon dwarfed our solar system. Its gravity shaped an entire galactic core. The accomplishment required linking radio observatories across Earth into a planet-sized instrument. Teams of scientists synchronized telescopes separated by continents. Data accumulated in enormous quantities. Years of analysis followed. The technical achievement was extraordinary. Yet hidden within the celebration was a subtle misunderstanding. The image did not actually show the black hole, it showed what happens around one. The distinction seems minor at first, but it is not. In fact, it may be one of the most important distinctions in modern astronomy. The dark region in the center of the image is often described as the black hole itself. This is understandable. The image encourages that interpretation. Human vision naturally treats dark shapes as objects. We see a silhouette and assume something occupies it. We see an outline and imagine a boundary. But the darkness is not the black hole. It is the shadow produced by the light being trapped near the event horizon. What we are seeing is not the thing itself. We are seeing the consequences of its existence. This difference matters because it reveals something profound about black holes. Even when we finally photograph them, we are still observing indirect evidence. The object remains hidden. The center remains inaccessible. The true nature of the black hole remains concealed behind a boundary no observation can cross. In a strange sense, the famous image did not eliminate mystery. It visualized mystery. It transformed an invisible question into a visible one. And once that realization settles in, a deeper discomfort begins to emerge. Because science often advances through observation. We study something. We collect information. The object becomes increasingly familiar. Uncertainty shrinks. Knowledge grows. Black holes refuse to cooperate with this pattern. The closer we get, the more sharply a fundamental limit appears. The event horizon is not simply a location in space. It is a boundary in knowledge. Knowledge? A horizon in the most literal sense. Just as a sailor standing on an ocean cannot see beyond Earth's curvature, observers outside a black hole cannot access information beyond the horizon. The universe itself seems to impose a restriction. There are things we can know, and things we cannot. This idea is psychologically unsettling because modern civilization is built upon the opposite assumption. We believe that ignorance is temporary, that mysteries eventually yield, that improved instruments and better theories gradually remove uncertainty. Black holes challenge this confidence, not because they're difficult, but because they may represent a category of reality that is fundamentally inaccessible. The distinction is important. A distant galaxy can be studied with larger telescopes. A microscopic particle can be examined with more powerful accelerators. But no amount of observational improvement allows information to escape an event horizon. The limitation is not technological. It is physical. Reality itself refuses access. And suddenly the black hole becomes more than an astronomical object. It becomes a reminder that knowledge may possess boundaries, that understanding may have edges, that the universe may contain regions forever beyond inspection. For centuries, humanity's store has been one of expanding horizons. We crossed ocean, mapped continents, explored planets, measured galaxies. Each generation inherited a larger universe than the one before it. The trajectory seemed obvious. The unknown would steadily retreat. Eventually, given enough time, perhaps everything could be understood. Black holes introduce doubt into that narrative, not because they are large, not because they are dangerous, but because they expose limits embedded within reality itself. And the deeper scientists examine those limits, the stranger the situation became. The event horizon initially appears straightforward. Cross the boundary and escape becomes impossible. Simple, elegant, final, yet simplicity can be deceptive. General relativity predicts the horizon beautifully. The equations describe its geometry with extraordinary precision. They explain how light behaves nearby, how time slows, how space-time bends, how gravity dominates. Everything appears mathematically coherent. But beneath this coherence lies a hidden problem. The equations describe what an outside observer sees. They do not necessarily explain what reality itself is doing. This distinction seems abstract until one follows it to its conclusion. Imagine watching an astronaut approach a black hole. From the astronaut's perspective, something remarkable happens. They continue falling. Nothing dramatic occurs exactly at the horizon. No visible wall appears. No cosmic signpost announces arrival. The journey continues. Yet from the perspective of a distant observer, a different story unfolds. The astronaut appears to slow. Signals arrive more slowly. Time stretches. The image fades. The astronaut seems frozen near the horizon. Two descriptions, both mathematically valid, both derived from the same physical laws, and yet they create radically different intuitions about reality. Did the astronaut cross the horizon? Did they remain outside it forever? What actually happened? Physics provides answers, but those answers become increasingly subtle and difficult to interpret. And this is where the familiar picture begins to fracture, because most people imagine black holes as objects existing inside the universe. A strange kind of object, certainly, but still an object. Something possessing a location, a boundary, and an interior. The mathematics suggests a more complicated possibility. Black holes may be less like objects and more like consequences. Consequences of space-time geometry itself. Consequences of how reality behaves under extreme conditions. Consequences of gravity pushed beyond ordinary intuition. If this interpretation is correct, then many popular images become misleading. The black hole is not a cosmic hole punched through space, not a tunnel, not a giant vacuum cleaner, not even necessarily an object in the ordinary sense. Instead, it may represent a region where our everyday concepts cease functioning properly, a place where language itself begins failing. And that failure is revealing, because whenever language breaks, it often indicates that intuition has reached its limits. The universe is no longer behaving according to human expectations. It is behaving according to deeper rules. Rules that evolved long before observers existed. Rules that do not care whether they feel intuitive. The famous image of a black hole therefore contains an unexpected lesson. The glowing ring is real. The shadow is real. The measurements are real. The science is real. Yet the closer the image appears to bring us to certainty, the more clearly it reveals how much remains hidden. We did not photograph understanding. We photographed a boundary, a silhouette marking the edge of knowledge. And beyond that edge lies the possibility that the black hole itself is not what we think it is, that our most familiar picture may be incomplete, and that the real mystery begins precisely where the image ends. Once the familiar image begins to dissolve, another transformation takes place. The black hole stops feeling like an isolated object. It stops feeling like a curiosity hidden in some distant corner of the cosmos, and it begins to reveal its true scale, not its physical size, its significance. Because one of the most persistent misconceptions about black holes is that they are rare, exotic, unusual, exceptions to the normal behavior of the universe. This intuition is understandable. After all, black holes occupy a peculiar place in popular culture. They are presented as extremes. The most powerful, the most dangerous, the most mysterious. The universe appears full of stars, planets, nebulae, and galaxies. Black holes seem like isolated oddities scattered among them. But the deeper astronomers looked, the less true that picture became. Again and again, evidence pointed toward a more unsettling reality. Black holes are not merely participants in cosmic history. They may be among its primary architects. And this is where scale becomes psychologically dangerous, because the human mind naturally treats importance and visibility as connected. Things that matter should be obvious. Things that shape events should be easy to identify. In everyday life, this assumption often works. A mountain dominates a landscape. A city dominates a region. A storm dominates a horizon. Influence announces itself. The universe operates differently. Some of its most influential structures are almost entirely hidden. To understand why, it helps to begin with a single star. Imagine a massive star living and dying somewhere in the Milky Way. For millions of years it burns through nuclear fuel, then collapse begins. The star explodes. A black hole forms. At first glance, this seems like the end of a story. A star existed. Now it does not. Its life has concluded. But nature rarely wastes consequences. The death of a massive star becomes the beginning of something else. The newly formed black hole immediately begins interacting with its environment. Nearby gas responds to gravity. Dust shifts. Matter falls inward. Energy emerges. Space itself becomes organized around the presence of an invisible mass. The black hole starts shaping its surroundings, not dramatically, not instantly, but persistently. Gravity is patient. Given enough time, patient forces become dominant forces. This lesson appears repeatedly throughout cosmic history. Entire galaxies form over billions of years. Stars migrate through gravitational interactions. Clusters emerge. Structures evolve. Everything changes slowly enough to feel motionless from a human perspective. Yet over immense timescales, subtle influences reshape reality. Black holes participate in this process at every level. And as astronomers expanded their observations, they discovered something astonishing. The largest black holes were not merely large. They were absurdly large. The supermassive black hole at the center of the Milky Way contains roughly 4 million times the mass of the Sun. That number is already difficult to visualize, but it is modest compared to some of the giants found elsewhere. In distant galaxies, astronomers discovered black holes weighing billions of solar masses. Some accumulated more mass than entire collections of stars once thought unimaginably vast, and these monsters existed surprisingly early in cosmic history. This discovery created a problem, because according to traditional models, growing something so enormous should require tremendous amounts of time. Yet the early universe appears to contain supermassive black holes that formed with alarming speed. The cosmos, it seemed, had assembled giants before it should have been possible. And whenever reality behaves faster than expected, scientists become uncomfortable. Not because the observation is unwelcome, but because it suggests missing information, a hidden mechanism, an incomplete theory, something fundamental yet undiscovered. This pattern has repeated throughout science. Unexpected planetary motion revealed unseen planets. Unexplained starlight revealed new physics. Anomalies often become signposts, indicators pointing toward deeper layers of reality. Supermassive black holes may represent one such signpost, because their existence forces an unsettling question. What if black holes are not merely products of cosmic evolution? What if they help drive it? Consider a galaxy. From a distance, it appears serene. A vast spiral of stars rotating through darkness. Elegant, stable, timeless. Yet appearances conceal violence. Stars are born. Stars die. Gas clouds collide. Radiation floods interstellar space. Gravitational forces reshape entire regions. Galaxies are dynamic ecosystems evolving over billions of years, and near their centers, black holes exert influence far beyond what their physical size suggests. Matter falling towards a supermassive black hole does not simply disappear. Before crossing the horizon, it forms an accretion disk. Gas accelerates. Temperatures rise. Magnetic fields twist. Extraordinary amounts of energy emerge. In some cases, enormous jets erupt from galactic centers. These jets can extend thousands or even millions of light years into surrounding space. Their scale is almost impossible to emotionally process. Imagine a beam of energy stretching so far that human civilization could rise and vanish countless times while its light continued traveling. Imagine structures larger than entire galaxies. Imagine forces operating for millions of years without interruption. This is not science fiction. These phenomena are observed across the universe, and they reveal something surprising. Black holes are not passive consumers. They are active participants. In some circumstances, they regulate star formation. In others, they alter galactic evolution. Their influence can extend far beyond their immediate surroundings. A hidden object no larger than the solar system can affect structures containing hundreds of billions of stars. The imbalance feels almost paradoxical. Tiny center, immense consequences, invisible source, visible transformation, and once again reality violates info. What appears small may dominate what appears vast. What appears empty may organize what appears full. The deeper one examines the cosmos, the more common this pattern becomes. Yet the scale continues expanding. Galaxies themselves are not isolated. They belong to clusters. Clusters belong to larger structures. The universe forms an enormous cosmic web spanning unimaginable distances. Galaxies gather along filaments of matter stretching across hundreds of millions of light years. Between them lie vast voids, regions so empty that loneliness acquires physical form. A spacecraft crossing such a void would travel through darkness beyond anything human beings have ever experienced. Not darkness caused by night, darkness caused by absence. Absence of stars, absence of galaxies, absence of almost everything. Against this backdrop, black holes begin appearing less like isolated anomalies and more like recurring features embedded throughout cosmic architecture. Everywhere astronomers look, they find evidence of gravitational collapse, evidence of hidden mass, evidence of invisible centers organizing visible structures, and this creates an uncomfortable philosophical shift. Because the universe many people imagine is fundamentally luminous, a cosmos built from stars, nebula, galaxies, light. The universe astronomy increasingly reveals is different. Much of reality is dark. Much of reality is hidden. Much of reality becomes visible only through its effects. Black holes occupy a special place within this realization because they concentrate the lesson into a single object. They remind us that visibility is not importance, that observation is not comprehension, that the most influential things in existence may remain inaccessible. And the farther outward we expand our perspective, the more significant that lesson becomes. A single black hole becomes a galactic phenomenon. Galactic phenomena become cosmological phenomena. The scale keeps growing. The implications keep deepening, and eventually a disturbing possibility emerges. Perhaps black holes are not simply strange objects embedded within an otherwise understandable universe. Perhaps they show clues pointing toward the principles that govern reality on scales far larger than humanity originally imagined. Because if these invisible structures helped shape galaxies, influenced cosmic evolution, and emerged throughout the universe with extraordinary consistency, then understanding black holes is no longer a niche scientific problem. It becomes part of a much larger question. A question about how the universe organizes itself. A question about why structure emerges from chaos. A question about whether the darkness scattered throughout the cosmos is more fundamental than the light surrounding it. And if that possibility is true, then black holes are not sitting at the margins of reality. They are much closer to its center than we once believed. The remarkable thing about black holes is not that they are mysterious. Many things in science remain mysterious. Dark matter remains unidentified. Dark energy remains unexplained. The origin of life remains uncertain. Mystery alone is not unusual. What makes black holes different is that they emerge from one of the most successful scientific theories ever created. A theory Sakya, that its predictions have been confirmed repeatedly for more than a century. A theory that describes planets, stars, galaxies, gravitational waves, and the expansion of the universe with astonishing precision. That theory is general relativity, and for a long time its success seemed almost miraculous. When Albert Einstein completed the theory in 1915, he transformed humanity's understanding of reality. Before relativity, space and time were generally viewed as separate backgrounds. Events occurred within them. Objects moved through them. The universe possessed a stage, and matter performed upon it. Einstein overturned that picture. Space and time became a unified structure, a dynamic fabric, not passive, not fixed, responsive. Matter and energy influenced space-time. Space-time influenced matter and energy. Reality became a relationship rather than a container. The idea was difficult to visualize. It still is. Human intuition evolved for forests, rivers, mountains, and changing weather. It did not evolve for four-dimensional geometry. Yet despite its strangeness, the theory worked. Again and again, light bent around massive objects exactly as predicted. Time flowed differently in strong gravitational fields. Orbits behaved correctly. Observations matched equations with extraordinary accuracy. The universe appeared to be confirming Einstein's vision. This success created confidence. Perhaps even more than confidence, it created trust. Scientists trusted general relativity because reality itself seemed to trust it. The equations continued succeeding wherever they were tested, and black holes emerged naturally from those equations. Not as an arm here, an optional feature. Not as an artificial addition, as a consequence. Given sufficient mass and sufficient collapse, space-time inevitably formed an event horizon. The mathematics was clear, the predictions were consistent, observations increasingly supported them. Everything seemed coherent, yet hidden inside this success was an unexpected warning. A warning so subtle that it remained largely ignored for decades. The equations worked beautifully almost everywhere, but not everywhere. There existed certain locations where something peculiar happened, certain conditions under which the mathematics itself began behaving strangely. The problem appeared at the very center of a black hole, the singularity. Few scientific terms carry as much psychological weight. It sounds mysterious, almost mythical, yet its technical meaning is even more unsettling. A singularity is not an object. It is not a physical substance. It is a place where the equations stop producing meaningful answers. A place where quantities become infinite, density becomes infinite, curvature becomes infinite. The mathematics effectively declares defeat. This is a profound statement, because infinity rarely appears in successful physical theories. Whenever scientists encounter infinities, they usually interpret them as signs that something is wrong, not necessarily with reality. With the model, imagine creating a map of Earth and discovering that one region expands into an infinitely large shape. The obvious conclusion would not be that the planet contains an actual infinite landscape. The obvious conclusion would be that the map has reached its limits. Something important is missing. Something needs correction. Black hole singularities produce a similar suspicion. General relativity predicts them, yet many physicists believe they signal the point at which the theory ceases to be complete. The implications are extraordinary, because general relativity is not merely a useful model. It is arguably one of humanity's greatest intellectual achievements. If even this theory fails under extreme conditions, then reality may be stranger than our most successful descriptions, and the evidence becomes increasingly difficult to ignore. The closer physicists examined black holes, the clearer the tension became. General relativity describes gravity extraordinarily well. Quantum mechanics describes the microscopic world extraordinarily well. Each theory dominates its own domain. Each predicts observations with astonishing precision. Yet the two refuse to merge cleanly. This incompatibility lies at the heart of modern physics. For decades, scientists have searched for a framework capable of uniting them. A theory of quantum gravity, a deeper description beneath both. So far, no universally accepted solution exists. And black holes sit directly at the center of the problem, because black holes combine enormous mass with extreme compression. They force gravity and quantum effects into close proximity. They create conditions where neither theory can comfortably ignore the other. The result is intellectual turbulence, a region where our most trusted ideas begin colliding. To appreciate how strange this is, consider what these theories represent. General relativity governs planets, stars, galaxies, and the large-scale structure of space-time. Quantum mechanics governs atoms, particles, fields, and the microscopic foundations of matter. Together, they explain nearly everything humanity has ever observed. Technology depends upon them. Modern civilization depends upon them. Their predictive power is beyond dispute. Yet inside a black hole, they disagree about reality. Imagine constructing two maps of the same city. Each map works perfectly. Each successfully guides travelers. Each accurately predicts roads and landmarks. Then one day you compare them and discover that the city centers are entirely incompatible. The maps cannot both be correct. Some deeper explanation must exist. Black holes produce a similar intellectual crisis. They expose the possibility that our understanding remains fragmented. Successful but incomplete, powerful but unfinished. This realization carries emotional weight beyond science itself. Human beings naturally seek coherence. We want reality to fit together. We want explanations to converge. We want knowledge to form a unified picture. Black holes quietly resist this desire. The closer we approach them, the more clearly the seams become visible. The hidden joins between theories. The unresolved contradiction, the places where understanding becomes uncertain, and uncertainty is unsettling precisely because it follows success. If black holes had always been mysterious, their ambiguity would feel ordinary. Instead, they emerge from a theory that appears almost perfect. They arise at the edge of triumph, at the point where confidence should be strongest. This is what makes them psychologically powerful. They remind us that success does not guarantee completeness. A theory can explain vast portions of reality and still fail under extreme conditions. An intellectual framework can transform civilization and still possess hidden limitations. Knowledge can advance enormously while remaining unfinished. This lesson becomes even more significant when viewed cosmically. The observable universe spans distances so immense that light has traveled for billions of years before reaching us. Galaxies drift through expanding space-time. Stars are born and die. Structures evolve across epochs almost impossible to imagine. General relativity successfully describes much of this grandeur. It allows humanity to reconstruct cosmic history, to understand gravitational waves, to predict black hole mergers, to map the geometry of the universe itself. And yet, somewhere behind an event horizon, the theory begins to falter. Not catastrophically, not visibly, but fundamentally. The equations continue pointing towards a destination they cannot properly explain. A singularity, an infinity, a region where mathematics ceases behaving like physics. And that raises an unsettling possibility. Perhaps black holes are not merely objects predicted by relativity. Perhaps they are messages from beyond relativity. Indicators pointing toward a deeper layer of reality still hidden from view. Because whenever a successful theory encounters a boundary, history suggests that something larger waits beyond it. Newtonian gravity worked beautifully until relativity expanded the picture. Classical physics worked beautifully until quantum mechanics expanded the picture. Every intellectual revolution begins with limits, with anomalies, with places where understanding stops. Black holes may represent exactly such a place. Not the end of knowledge, or the edge of a map, a horizon beyond which a deeper reality remains concealed. And if that is true, then the most important feature of a black hole is not its gravity, not its darkness, not even its event horizon. The most important feature may be the singularity itself. Not because we know what it is, but because we do not. A silent marker placed by the universe at the edge of comprehension, a place where our greatest theory finally admits uncertainty, and where the next chapter of understanding may eventually begin. For a while, it seemed possible that black holes were simply difficult. Difficult mathematics, difficult observations, difficult environments, but ultimately understandable. The event horizon marked a boundary. Matter fell inward. Gravity dominated. A singularity formed. The story appeared strange yet coherent. Then physicists discovered a problem so unsettling that it threatened not merely our understanding of black holes, but our understanding of reality itself. The problem began with a simple question. What happens to information? At first glance, the question sounds almost trivial. Information feels abstract, secondary, less important than matter or energy. Yet modern physics treats information very differently. Information is not merely knowledge. It is physical. It describes the state of reality itself. The position of particles, their motion, their interaction, the arrangement of matter and energy throughout the universe. Change the information and you change the physical system. And according to one of the deepest principles in physics, information cannot simply disappear. This idea is woven throughout quantum mechanics. The microscopic world evolves according to precise mathematical rules. Those rules allow information to change form, to spread, to become scrambled, to become extraordinarily difficult to recover, but not to vanish. In principle, the information remains present. Hidden, perhaps, dispersed, perhaps, yet preserved. This principle lies beneath much of modern science. Without it, prediction becomes unstable. Causality weakens. Reality itself becomes harder to describe. The universe appears to remember its own history. Not perfectly from a human perspective, but fundamentally. Then black holes entered the discussion, and suddenly that comforting assumption began to collapse. Imagine throwing a book into a black hole. The book contains information, words, ink patterns, molecular structures, atomic arrangements. Every detail contributes to its physical state. Now imagine throwing an entire library into the black hole, then a planet, then a star, then an entire civilization. Everything crosses the horizon. Everything disappears from view. The black hole grows slightly larger, but the specific information describing what fell inside appears lost. At first, physicists were not particularly concerned. After all, information still existed inside the black hole. The universe had not forgotten. The information had merely become inaccessible, hidden beyond the horizon. Problem solved. Or so it seemed. Then, in the 1970s, a remarkable discovery changed everything. A discovery made by Stephen Hawking. Until that point, black holes appeared almost eternal. They could grow. They could merge. They could persist for immense periods of time. But Hawking realized something unexpected. Quantum mechanics altered the picture. According to his calculations, black holes should slowly emit radiation. Tiny amounts at first, almost imperceptible, but real. This phenomenon became known as Hawking radiation. The implications were astonishing. Black holes were not eternal after all. They could evaporate. Given enough time, they could disappear completely. For stellar mass black holes, the process requires periods of time so immense that ordinary language struggles to describe them. Not thousands of years, not millions, not billions, numbers so large that entire cosmic eras pass before the process completes. Yet eventually, according to the calculations, the black hole vanishes. And this is where the crisis emerges. Because if the black hole disappears entirely, what happens to the information? The book, the library, the planet, the civilization, every particle that crossed the horizon? Where does the information go? Hawking's original calculation suggested a disturbing answer. Nowhere. The information appeared destroyed, not hidden, not scrambled, gone, erased from reality. This conclusion struck physics like a fracture spreading through glass, because it directly contradicted quantum mechanics. Two of humanity's greatest theories suddenly produced incompatible answers. General relativity permitted the black hole. Quantum mechanics demanded information preservation. Hawking radiation appeared to destroy information. The contradiction could not simply be ignored. Something had to give. Either quantum mechanics was incomplete, or general relativity was incomplete, or black holes were not what we thought they were. Perhaps all three. The situation became known as the black hole information paradox. The name sounds technical, almost academic, yet beneath the terminology lies a profoundly unsettling implication. The paradox asks whether reality forgets, whether history can truly disappear, whether causes can lose connection with effects, whether the universe preserves itself or slowly erases parts of its own story. For decades, physicists argued intensely over the answer, not because they enjoyed agreement, because the stakes were enormous. The paradox threatened the coherence of modern physics, and black holes sat directly at the center. What makes the problem psychologically powerful is its familiarity. Human beings already struggle with impermanence. Memories fade, records decay, civilizations disappear, languages vanish, entire cultures dissolve into fragments, histories full of loss. The information paradox transforms this human experience into a cosmic one. It asks whether reality itself suffers from forgetting, whether the universe ultimately preserves what happens within it, or allows pieces of existence to vanish forever. The question becomes even more unsettling when translated into human terms. Every person who's ever lived represents an extraordinary arrangement of matter and information. Every thought, every memory, every conversation, every moment of consciousness. Physics describes these experiences through physical states, particles, fields, structures. If information can truly disappear, then reality may be more fragile than we assume. The universe may not simply forget civilizations, it may forget events themselves. The possibility feels deeply wrong. And many physicists believe it is wrong. Over the years, countless proposals emerged. Some suggested information remains encoded in Hawking radiation. Others proposed that information is stored on the event horizon itself. Some argued that subtle quantum effects preserve the missing details. Others proposed entirely new frameworks. The debate continues. No single explanation commands universal agreement. Yet something remarkable happened during the search. Attempts to solve the paradox began revealing unexpected connections. Connections between gravity and information, between spacetime and quantum theory, between geometry and computation. The deeper scientists investigated, the more reality began resembling something stranger than classical intuition ever anticipated. Information stopped appearing secondary, it began appearing fundamental. Some modern approaches suggest that space-time itself may emerge from deeper informational relationships. That geometry could be built from entanglement, that gravity might arise from principles more abstract than matter alone. These ideas remain active areas of research. Many questions remain unresolved, yet their existence reveals something important. Black holes have transformed from objects of study into engines of discovery. Not because they provide answers, because they expose weaknesses. They force physics into uncomfortable territory. They reveal assumptions that otherwise remain hidden. The information paradox exemplifies this perfectly. The problem originated with a seemingly simple question. What happens to information that falls into a black hole? Yet following that question leads directly toward the foundations of reality, toward the structure of space-time, toward quantum theory, toward the possibility that the universe operates according to principles far deeper than previously imagined. And this is why black holes have become so significant, not because they're the most dangerous objects in existence. Danger is a human concern. The cosmos is indifferent to such categories. Black holes matter because they expose limits. Limits in theory, limits in observation, limits in understanding. Every time physicists attempt to explain them completely, another contradiction emerges. Another hidden assumption becomes visible. Another layer of reality reveals itself. The process resembles descending into darkness with a lantern. Each step illuminates something new, yet each step also reveals how much darkness remains. And perhaps the most unsettling realization is this. The information paradox may not be a problem created by black holes. It may be a problem created by us. a sign that the conceptual tools humanity uses to understand reality are still incomplete, a sign that our categories space, time, matter. Information may not be as fundamental as they appear. If that is true, then black holes are not merely cosmic objects. They are mirrors reflecting the limitations of human understanding back toward us. And the deeper we stare into them, the harder it becomes to determine whether the mystery belongs to the black hole itself, or to the framework through which we attempt to understand it. Eventually, every investigation reaches a point where familiar language begins to fail, not because the subject becomes complicated. Complicated things can still be described. A jet engine is compliqué. A living cell is complicated. A galaxy is completor. Compliced. Complexity alone does not defeat language. The problem arises when reality stops resembling the categories language was built to describe. Black holes occupy precisely that territory, and nowhere is this more apparent than near the singularity. For decades, the singularity has existed as both a prediction and a warning. A prediction because the mathematics of general relativity leads toward it. A warning because the mathematics becomes pathological upon arrival. At the center of a black hole, the equations predict that density becomes infinite, curvature becomes infinite. The structure of space-time itself collapses into a point of zero volume and effectively limitless gravitational intensity. The word infinite appears again and again, and physicists grow suspicious whenever it does. Infinity is useful in mathematics. Reality is less cooperative. No experiment has ever measured an actual infinity. No observation has ever revealed a physically infinite quantity. Whenever infinities emerge inside a theory, they often indicate that the theory has ventured beyond its domain of reliability. Like a compass spinning wildly near a magnetic disturbance. The instrument still functions. The environment has become unsuitable. This is why many physicists do not believe singularities literally exist, not in the way the equations describe them. The singularity is often interpreted as a marker, a signpost, a place where general relativity reaches the edge of its authority. Beyond that edge, some deeper theory must take over. The question is what that deeper theory looks like, and this is where the intellectual landscape becomes increasingly strange. Because black holes force two radically different descriptions of reality into direct confrontation. General relativity governs the large-scale universe. Quantum mechanics governs the microscopic one. Under ordinary circumstances, the separation works remarkably well. Stars and galaxies follow relativistic rules. Atoms and particles follow quantum rules. Each theory dominates its own territory. But black holes erase the boundary. Immense mass is compressed into astonishingly small regions. Gravity becomes overwhelming. Quantum effects become unavoidable. The two frameworks collide, and reality refuses to explain how the collision resolves. To appreciate how extraordinary this situation is, imagine two maps of the world. One accurately describes every mountain, river, and continent. The other accurately describes every city, road, and building. Both work perfectly. Both predict observations. Both guides travelers successfully. Then you discover that the maps become incompatible at the center of the world. They cannot both be correct, yet neither appears wrong. The contradiction demands something deeper, something capable of explaining both. This is the situation modern physics faces, and black holes occupy the disputed territory. The closer scientists approach the horizon, the more apparent the conflict becomes. Because quantum mechanics describes a universe fundamentally different from the one suggested by everyday experience. Particles behave like waves. Probabilities replace certainties. Entanglement connects systems across enormous distances. Reality becomes less solid and more relational, less object-like and more informational. These ideas already challenge intuition, yet black holes push them further. The information paradox, discussed earlier, suggested that information might somehow survive processes that appear destructive. Attempts to resolve that paradox produced increasingly radical possibilities. One proposal became especially unsettling. Perhaps the event horizon is not empty. Perhaps it is not merely a geometric boundary. Perhaps it possesses structure, information, activity, something hidden from classical descriptions. Over time, these ideas evolved into a collection of theories that transform the horizon from a passive boundary into something far stranger. Some physicists proposed that information is encoded across the horizon itself. Others suggested that reality behaves holographically. The word sounds almost poetic, but the idea is remarkably pressing. A hologram allows three-dimensional information to be encoded on a two-dimensional surface. The holographic principle applies a similar concept to the universe. It suggests that the information describing a region of space may be stored on its boundary. The implications are difficult to emotionally absorb because they challenge one of the most basic assumptions humans possess. We assume reality exists where it appears to exist. Objects occupy volume. Events occur inside space. Three-dimensional existence feels obvious. The holographic perspective introduces doubt. What if volume is not fundamental? What if depth emerges from more primitive relationships? What if the universe resembles a projection generated from information encoded elsewhere? These ideas remain areas of active research. They are not established facts, yet they arise from series of attempts to resolve serious problems, and that alone is revealing. The path toward understanding black holes repeatedly forces science into territory that sounds almost impossible. Not because scientists desire exotic explanations, because conventional explanations keep encountering limits. The deeper researchers travel, the stranger reality appears willing to become, and then there is time. Perhaps the most psychologically destabilizing aspect of all. Human experience is built upon temporal order. Moments arrive. Moments pass. The future becomes the present. The present becomes the past. Everything familiar depends upon this flow. Black holes distort time in ways that challenge the very foundations of that intuition. Near an event horizon, time behaves differently, not metaphorically, physically. A clock falling toward a black hole does not agree with a clock far away. The disagreement is measurable, real, predicted by relativity and confirmed in less extreme environments throughout the universe. The closer one approaches intense gravity, the more severe the effect becomes. Eventually, the divergence grows extraordinary. To a distant observer, processes near the horizon appear slowed. Signals stretch. Events unfold differently. Time itself loses the universal character that common sense assigns to it. This realization is profound because it reveals something hidden within everyday life. Human beings often imagine time as a cosmic background, a universal river flowing equally for everything. Relativity dismantled that picture long ago. Black holes merely make the consequences impossible to ignore. The universe possesses no master clock, no universal present, no single timeline shared by all observers. Reality is more fragmented, more local, more dependent upon perspective. And once again, intuition collapses. The familiar concepts remain useful at ordinary scales. Yet under extreme conditions they fail. The deeper one examines black holes, the more common this pattern becomes. Space behaves differently. Time behaves differently. Information behaves differently. Causality becomes subtle. Geometry becomes dynamic. The distinction between physical and mathematical description begins to blur. What initially appeared to be a strange object now resembles a crossroads. A place where multiple foundations of reality intersect. A place where every major theory encounters pressure. A place where certainty weakens. This transformation changes the emotional character of the subject. At first, black holes seem frightening because of their gravity, then because of their darkness, then because of their scale. Eventually, a deeper discomfort emerges. The discomfort of epistemology. The discomfort of not knowing whether our conceptual framework is adequate. The discomfort of realizing that humanity's greatest theories may be approximations rather than final truths. This realization is not unique to black holes. Science has encountered similar moments before. Every major revolution began with anomalies, with contradictions, with observations that existing theories could not comfortably explain. But black holes differ in one important respect. The contradictions occur at the heart of modern physics itself, not at the margins, not in obscure details. at the intersection of our most successful descriptions of reality, and that is why the stakes feel so large. Because if black holes expose flaws in our understanding, those flaws may extend far beyond black holes. They may reach into the nature of space-time, the nature of information, the nature of causality, perhaps even the nature of existence itself. The singularity then becomes more than a mathematical curiosity. It becomes a symbol, a marker placed at the edge of knowledge, a reminder that beneath the apparent solidity of scientific understanding lies uncertainty, not ignorance in the ordinary sense, something deeper, a recognition that reality may possess layers still hidden from view. And if that recognition's correct, then black holes are not merely destinations where matter falls inward. They are thresholds beyond which the universe begins revealing how incomplete our understanding may truly be. There is a particular comfort hidden inside ordinary human experience, a comfort so familiar that it usually goes unnoticed. The world appears, but distances remain fixed. Time moves forward. Objects possess locations. Events possess causes. The future arrives gradually. Reality feels continuous, coherent, trustworthy. Most of civilization is built upon this confidence. Every road, every city, every calendar, every conversation depends upon assumptions so deeply embedded that questioning them feels unnecessary. Even modern science, despite all its revelations, often preserves this emotional foundation. Planets orbit stars orbit galaxies. Galaxies move through expanding space. The scales become larger, but the underlying logic remains recognizable. Reality continues behaving like a place somewhere. Black holes slowly dismantle that intuition, not through violence, not through spectacle, but through implication, because once the physics surrounding them is followed carefully enough, something unsettling begins to happen. The categories through which human beings understand existence start losing their clarity. At first, the change seems manageable. Time slows near strong gravity. That idea is already familiar to many people. Clocks near massive objects tick differently than clocks farther away. The effect is measurable. GPS satellites must account for it. Relativity has confirmed it repeatedly, yet familiarity conceals the true significance. Because the statement "time slows" sounds as though time itself remains a thing that can speed up or slow down. A universal substance, a cosmic flow. In reality, relativity suggests something stranger. There is no universal flow, no master clock, no single present shared throughout the universe. The now you experience is not a universal event. It is local, personal, bound to your position and motion through space-time. This realization already stretches intuition. Black holes push it much further. Imagine two observers. One remains safely distant. The other falls toward an event horizon. Both carry clocks. Both observe reality. Both experience time normally from their own perspectives, yet their descriptions of events increasingly diverge. The closer the falling observer approaches the horizon, the more dramatically their experiences separate. To the distant observer, time near the black hole appears distorted. Signals become stretched. Process is slow. Images fade. The falling observer seems trapped near the horizon, suspended, frozen, never quite crossing. And yet from the perspective of the falling observer, nothing extraordinary occurs at that precise boundary. The journey continues. The horizon is crossed. Time moves forward. Reality remains locally normal. Both descriptions emerge from the same theory. Both are mathematically valid. And this is where intuition begins to collapse. Because human beings instinctively assume there must be one correct account, one true version of events, one objective narrative. Relativity refuses to provide it. Reality becomes dependent upon perspective in ways that common sense struggles to accept. The discomfort deepens when we examine causality. Causality feels fundamental. Causes produce effects. Actions create consequences. The sequence seems unavoidable. Indeed, much of rational thought depends upon it. Without causality, explanation itself becomes impossible. Yet near black holes, the structure supporting causality becomes increasingly strange. The event horizon divides the universe, not merely physically, informationally. Observers outside the horizon lose access to regions beyond it. Future events become constrained. Possible paths narrow. The geometry of space-time itself shapes what can influence what. This is difficult to visualize because human beings rarely experience geometry as destiny. A mountain may block movement, an ocean may limit travel, but space-time itself does not normally feel restrictive. Near a black hole, it does. The geometry becomes so extreme that all possible futures point inward. Not metaphorically, literally. Every available path leads deeper. The distinction between direction and destiny begins to blur, and suddenly space no longer behaves like a passive stage. It becomes an active participant in reality. This shift carries profound philosophical consequences. Human intuition evolved within a narrow range of conditions. Weak gravity, moderate velocities, short time scales, small distances. The universe beyond those conditions may not resemble human expectations at all. Black holes expose this possibility with unusual clarity. They reveal how many assumptions depend upon local circumstances. What feels fundamental may be provincial. What feels universal may be temporary. What feels obvious may merely reflect the environment in which intelligence evolved. This realization has appeared before in science. Earth is not the center of the cosmos. The sun is not unique. The Milky Way is not central. Again and again, humanity discovers that familiar perspectives are limited. Black holes continue that pattern, but now the target is not our location. It is our intuition. The challenge becomes psychological. Can a mind shaped by everyday experience truly understand realities that violate the conditions under which it evolved? Can language designed for ordinary life adequately describe horizons, singularities, and relativistic spacetime? Can common sense survive contact with extreme physics? The answer appears increasingly uncertain, and nowhere is this uncertainty more visible than in the concept of distance. Distance seems straightforward. Two objects occupy separate positions. Measure the gap. Problem solved. Black holes complicate even this. Inside general relativity, space-time itself becomes dynamic. Distances depend upon geometry. Geometry depends upon mass and energy. The structure of reality becomes flexible, stretchable, curved. The familiar certainty of measurement begins to weaken. Even the concept of location becomes subtle. Where exactly is a black hole? The question sounds simple, yet the answer becomes surprisingly complicated. Is the black hole the event horizon, the singularity, the surrounding gravitational field, the trapped region of space-time? Different contexts produce different answers. The object resists clean categorization, and this resistance matters because categorization is one of humanity's primary tools for understanding. We define things, separate them, assign boundaries. Black holes repeatedly challenge those boundaries. Object and geometry blur together. Information and physics intertwine. Observer and observation become difficult to separate. The closer one looks, the less stable the categories appear. Eventually, a larger realization emerges. The challenge posed by black holes may not be primarily scientific. It may be cognitive. Human beings instinctively imagine reality as composed of things. Black holes increasingly suggest that relationships may be more fundamental than things. Geometry, information, connection, structures. The universe begins to resemble a network rather than a collection of objects, a process rather than a collection of places, a pattern rather than a stage. This perspective remains incomplete. Many questions remain unresolved. Yet the direction is revealing. The closer physics approaches the deepest layers of reality, the less familiar the landscape becomes, and that unfamiliarity carries emotional consequences. Civilization often assumes that knowledge produces certainty. That greater understanding leads to a more comfortable picture of existence. Black holes suggest the opposite. Greater understanding can reveal greater strangeness. The universe becomes less intuitive, not more, less anthropocentric, less accommodating, less aligned with ordinary experience. The effect is subtle but cumulative. Each realization seems manageable in isolation. Time is relative. Space is curved. Information behaves strangely. Horizons restrict observation. Viewed separately, these ideas appear merely unusual. Together they produce something larger, a gradual collapse of the intuitive universe. The comfortable mental model inherited from everyday life begins dissolving. What replaces it is not chaos. The universe remains lawful, predictable, mathematically structured, but it no longer feels familiar. Reality becomes something vast and indifferent, something operating according to principles that existed long before observers emerged, something that would continue unchanged if no observer existed at all. And perhaps that is the deepest lesson black holes offer. Not that the universe is hostile. Hostility requires intention. The universe appears far older than intention, far older than meaning, far older than perspective. Black holes merely expose this age more clearly than most phenomena. They reveal a reality that functions independently of human intuition, a reality whose deepest structures may have no obligation to resemble human expectations. And once that realization takes hold, another question begins to emerge. If black holes are already forcing us beyond the limits of intuition, what happens when we place them inside the even larger structures of the cosmos itself? Once black holes cease being isolated objects, the scale changes again, not gradually, not comfortably, but in a way that forces the mind outward. For most people, a black hole is imagined as a destination, a region of space, a dark object floating somewhere among the stars. Even after learning about event horizons, singularities, and relativistic time, it is still tempting to think of black holes as individual phenomena. Separate, self-contained, discrete, yet the universe rarely organizes itself around isolated things. Reality prefers systems, relationships, networks of influence extending across enormous distances. And when black holes are viewed within that larger context, they become something more than extreme objects. They become components of cosmic architecture. The change in perspective is subtle. At first, consider our own galaxy. The Milky Way contains hundreds of billions of stars. Most of those stars will never approach the central black hole. Most will spend their entire lives orbiting through the galactic disk, largely unaffected by the extreme environment near the core. At first glance, this seems to reduce the significance of Sagittarius, a star. After all, how important can an object be if most of the galaxy remains far away from it? The answer emerged slowly through decades of observation. Galaxies and their central black holes appear connected in ways nobody anticipated. The relationship is not merely one of proximity, it is one of coevolution. As astronomers measured galaxies across the universe, they discovered something surprising. The mass of a galaxy's central black hole often correlates with properties of the galaxy itself. Larger galactic bulges tend to host larger black holes. Smaller systems tend to host smaller ones. The pattern appears repeatedly, too consistently to dismiss as coincidence. It is as though the galaxy and the black hole grew together, as though each influenced the development of the other. This realization changed the conversation. Black holes were no longer viewed merely as consequences of galactic evolution. They appeared woven into the process itself. The implication was profound, because galaxies are among the largest organized structures in the universe. Their formation spans billions of years. Their evolution involves vast quantities of matter and energy. If black holes participate in that story, then their importance extends far beyond their immediate surroundings. And once again, the visible universe begins revealing hidden dependencies. The stars we see may not tell the whole story. The luminous structures dominating astronomical images may owe part of their existence to invisible centers that rarely appear directly, centers that shape reality from concealment. This pattern grows more striking when we move beyond individual galaxies. Galaxies gather into clusters. Clusters gather into superclusters. These structures are not random. They form part of a vast cosmic web extending across the observable universe. On the largest scales known, matter organizes itself into filaments and nodes, immense strands connecting concentrations of galaxies across hundreds of millions of light years. The image resembles a neural network, or frost spreading across glass, or roots extending through soil. The resemblance is coincidental, yet psychologically powerful, because it reveals something unexpected. The universe possesses structure at scales almost impossible to emotionally comprehend. A human lifetime disappears within such distances. Entire civilizations become invisible. Recorded history becomes shorter than a blink. The largest human achievements lose scale entirely. And yet these structures exist, silently, patiently, evolving across epochs so long that language begins to fail. Black holes occupy only tiny regions within this vast architecture, yet they appear everywhere the architecture becomes dense. Every major galaxy, every active galactic nucleus, every region where gravity has concentrated matter over immense periods of time, the recurrence is striking. Again and again, gravitational collapse emerges as a fundamental process. Again and again, black holes appear. It is almost as if the universe repeatedly rediscovers the same solution. Mass accumulates, gravity strengthens, collapse follows. The pattern repeats from stellar scales to galactic scales. Across billions of years, across billions of light years, the consistency suggests something important. Black holes may not be accidents. They may represent one of gravity's preferred outcomes, one of the natural endpoints toward which structure evolves. This possibility carries an unsettling implication, because if black holes are recurring features of cosmic evolution, then they are not marginal phenomena. They are woven into the fabric of cosmic history. The universe may be producing them continuously, quietly, relentlessly, not as exceptions, as consequences. And this raises a larger question. What role do they play in the future? Astronomy often focuses on origins, the birth of stars, the formation of galaxies, the emergence of structure. Yet the universe is not only a story of beginnings, it is also a story of endings. Stars exhaust their fuel, galaxies collide, matter disperses, entropy increases, time moves forward, the future of the cosmos stretches beyond imagination, and black holes occupy a central position within many visions of that future. Consider a timescale of trillions of years. Already the number exceeds ordinary comprehension. Civilization measures centuries. Biology measures millennia. Recorded history spans only a few thousand years. 1 trillion years belongs to an entirely different category of existence. Yet even that is only the beginning. Over such duration does gradually die. Star formation slows, galaxies age. The bright universe begins to dim. The cosmos that currently appears filled with light slowly changes character. Darkness becomes increasingly common, not because something destroys the stars, because stars are temporary. Eventually, many of the remaining luminous objects disappear, and black holes persist, patient, silent, long after most familiar structures have vanished. This is one reason some cosmologists describe black holes as among the last great monuments of the stellar universe. They may outlive nearly everything that created them. The thought is difficult to absorb. Human beings instinctively associate darkness with absence, with endings. Yet black holes transform darkness into endurance. The stars burn brightly but briefly. Black holes emit almost nothing and survive enormously longer. The contrast feels symbolic. Light announces itself. Darkness remains. And when projected across cosmic timescales, the symbolism becomes almost haunting. Imagine a future universe in which most stars have faded. Galaxies have evolved beyond recognition. The great luminous era of cosmic history has ended. Black holes remain among the dominant structures, not because they conquered the universe, because they endured it. The image is unsettling precisely because it inverts intuition. We assume brightness signifies permanence. We assume visibility signifies importance. Again and again, reality suggests otherwise. What is hidden may persist longer than what is seen. What is sudden may outlast what is loud. What appears empty may ultimately dominate. The larger cosmic system reinforces this lesson continuously. At every scale, black holes challenge assumptions about significance. They are physically small compared to galaxies, yet they influence galactic evolution. They are invisible, yet their effects shape visible structures. They occupy tiny fractions of cosmic volume, yet they may play disproportionate roles in the universe's long-term future. The pattern is unmistakable, and the emotional consequence is profound. The universe begins to feel less like a collection of objects and more like a hierarchy of hidden influences. Visible reality becomes only the surface. Beneath it lies a deeper layer of relationships, gravity guiding structure, information shaping possibility. Invisible centers organize invisible system. Black holes become symbols of this hidden layer, not because they explain everything, because they reveal how much remains concealed. And once this larger system comes into view, another realization follows. The cosmic web itself, immense as it appears, occupies only a small fraction of existence. Between its filaments lie vast regions of near emptiness, voids so enormous that entire clusters of galaxies become isolated islands separated by unimaginable darkness. And within those expanses, a new kind of perspective emerges. A perspective not defined by structure, but by absence, not by influence, but by isolation. A perspective in which the loneliness implied by black holes becomes inseparable from the loneliness of the universe itself. The deeper astronomy peers into the universe, the less crowded it becomes. This seems backward. Most people imagine exploration revealing abundance. New worlds, new stars, new galaxies. The farther outward we look, the more things we expect to find. And in one sense, that expectation is correct. The observable universe contains hundreds of billions of galaxies, perhaps more. Each galaxy contains enormous populations of stars. The total numbers exceed anything the human mind evolved to comprehend. Yet numbers can be deceptive, because abundance is not the same thing as closeness. And black holes, perhaps more than any other cosmic phenomenon, force us to confront the difference. Imagine standing on a beach at night. You look across a dark ocean. There may be countless grains of sand beneath the water, countless fish moving through the depths, countless molecules suspended in every wave. Look on every wave. The environment is rich with existence. Yet what you feel is not abundance. You feel distance. The darkness between yourself and whatever lies beyond sight dominates perception. The universe behaves similarly. Astronomical objects are numerous. The spaces between them are enormous. And as our perspective expands, those spaces begin to dominate the story. The nearest star beyond the Sun is approximately 4 light-years away. This fact is familiar, repeated in textbooks, mentioned in documentaries. Yet familiarity often conceals meaning. A light year is not merely a unit of distance. It is a unit of loneliness. It measures how long even light requires to cross the emptiness between stars. The photons arriving from that neighbouring star tonight began their journey years ago, long before most of today's headlines existed, long before countless human decisions were made, long before many children now alive took their first breath. And that is merely the nearest star. The distances separating galaxies are vastly greater. The distances separating clusters greater still. The universe is not primarily composed of stars, or planets, or galaxies. It's primarily composed of emptiness. Black holes intensify this realization because they occupy a peculiar relationship with emptiness itself. Their defining feature is not matter. It is absence of access. A horizon beyond which information cannot return, a region separated from the rest of reality by a fundamental limit. In this sense, black holes embody a principle already present throughout the cosmos: separation. Not absolute separation, but practical separation. The universe is full of regions that cannot meaningfully interact. Distances become too large. Signals require too much time. Light itself becomes too slow. The observable universe appears connected from a mathematical perspective. Emotionally, it resembles an archipelago of isolated islands, and the farther into the future we look, the stronger this impression becomes. Because cosmic expansion continues, for much of human history, expansion itself was unknown. The universe was often imagined as static, permanent, unchanging on the largest scales. Then observations revealed a startling that galaxies are receding from one another. Space itself expands. The cosmos is growing. At first, this discovery seemed merely surprising. Over time, as deeper implications emerged, expansion is not simply increasing distance. It's altering the future structure of reality. Some galaxies remain gravitationally bound to one another, others do not. Over immense spans of time, distant galaxies drift beyond observational reach. Not because they vanish, not because they are destroyed, because space between us and them expands too rapidly. Their light can no longer bridge the gap. The galaxies remain. The information does not arrive. The universe gradually becomes more isolated. This process unfolds on timescales far beyond human experience, yet the implication is profound. Future civilizations, if any exist, may inherit a smaller visible cosmos than we do. Not physically smaller, observationally smaller. Much of today's universe will eventually disappear beyond the cosmic horizon. The night sky itself will become less informative. The evidence of cosmic history will slowly fade. This possibility is strangely haunting. Humanity lives during a period when the universe remains unusually observable. Galaxies fill the sky. Cosmic history remains visible. Ancient light still arrives. Future observers may lose access to much of that information. Reality will not change. Perspective will, and once again, information becomes central. Black holes hide information behind horizons. Cosmic expansion hides information behind horizons. Different mechanisms, similar consequences. Knowledge encounters limit. Observation encounters boundaries. The accessible universe shrinks relative to the inaccessible one. The pattern repeats at multiple scales, and this repetition suggests something unsettling. Perhaps separation is more fundamental than connection. Human beings instinctively focus on links, relationships, communication, interaction. Civilization itself depends upon reducing isolation. Roads connect cities. Language connects minds. Technology connects continents. Progress often feels synonymous with overcoming distance. The universe appears less concerned with such ambitions. Distances remain immense. Communication remains limited by light. Horizons emerge naturally. Isolation is not an anomaly. It is a recurring feature of reality. Black holes reveal this feature dramatically because they concentrate it into a single object. The event horizon becomes a visible symbol of a broader truth. There are regions we cannot access, information we cannot retrieve, perspectives we cannot share. The principle extends far beyond black holes. It permeates the cosmos, and nowhere does this become more emotionally powerful than within the great cosmic voids. Between the filaments of the cosmic web lie enormous expanses containing very few galaxies. Some voids span hundreds of millions of light years. To cross such a region would require durations exceeding the entire history of human civilization many thousands of times over. Even travelling at the speed of light, the journey becomes immense. The darkness is not merely visual, it is structural, a consequence of sparse matter distributed across incomprehensible distances. When astronomers map these voids, the resulting images often appear beautiful, elegant, almost artistic, yet beneath that beauty lies something colder. The realization that most of the universe is astonishingly empty. Not empty in the absolute sense, empty relative to expectation. Empty relative to the density of human love. Empty relative to the environments in which consciousness evolved. Conscious beings arise in pockets, around stars, within galaxies, inside small regions where complexity can flourish. Beyond those islands stretches an ocean of separation. Black holes belong naturally within this landscape. not because they create loneliness, because they reflect it. They mirror a universe in which access is limited, information is local, perspective is constrained. The farther one travels into cosmic reality, the more evident these constraints become. This realization carries philosophical consequences. Human culture often assumes that understanding grows without limit. That knowledge expands steadily outward, that every mystery eventually yields to investigation. The cosmos suggests caution. Some regions may remain permanently inaccessible. Some information may remain forever hidden. Some aspects of reality may exist beyond any possible observation. Black holes remind us of this. Cosmic horizons reinforce it. The observable universe itself embodies it. Reality contains edges, not necessarily physical edges, epistemological edges, boundaries of knowledge, boundaries of observation, boundaries of participation. And once those boundaries become visible, the emotional character of existence changes. The universe no longer feels like a stage awaiting exploration. It begins to feel like an immense landscape of partial access, a reality in which every observer sees only fragments, a reality in which complete perspective may be impossible. Black holes are powerful not because they are unique, but because they reveal this condition with unusual clarity. They make ignorance visible. They transform limitation into geometry. They place a horizon directly before us and quietly demonstrate that some boundaries cannot be crossed. And when that lesson is expanded to the scale of galaxies, clusters, voids, and cosmic history itself, another possibility begins to emerge. Perhaps the deepest mystery is not what lies inside a black hole. Perhaps that the deeper mystery is whether any observer, anywhere, can ever possess a complete picture of reality at all. There is a difference between something being unknown and something being unknowable. Human history is largely a story of confusing the two. Ancient civilizations looked at the planets and saw wandering lights. They did not know what those lights were. The mystery felt immense, yet the mystery was only temporary. Telescopes improved. Mathematics advanced. Knowledge expanded. The planets moved from the category of unknown to the category of known. The same pattern repeated countless times. Lightning, disease, the age of Earth, the structure of galaxies, the composition of stars. Again and again, ignorance retreated, and with every retreat came a subtle philosophical assumption. If enough time passes, perhaps everything can eventually be understood. Perhaps every mystery is merely a future discovery waiting to happen. This belief is rarely stated directly, yet it quietly influences the modern imagination. The unknown becomes a challenge, a puzzle, a temporary absence of information. Black holes complicate that optimism, not because they remain mysterious. Mysteries alone do not threaten the assumption. What threatens the assumption is the possibility that some questions may possess no observational path toward resolution. Not difficult questions, unreachable questions separated from us not by technological limitations, but by the structure of reality itself. The distinction is profound. Imagine a locked room. You cannot see inside. The contents remain unknown, but the room can be opened. The obstacle is practical. Now imagine a room that no signal can ever leave. No light, no sound, no information of any kind. The obstacle becomes fundamental. The difference between ignorance and impossibility begins to matter. The event horizon introduces exactly this tension. It's often described as a boundary beyond which escape becomes impossible. That description is accurate, yet it hides a deeper implication. If information cannot escape, then observation cannot proceed. And if observation cannot proceed, knowledge encounters a limit. This realization creates discomfort because modern science depends upon observation. Evidence must flow outward. Measurement in the response must be possible. Signals must arrive. Without information, scientific investigation cannot function. Black holes place a portion of reality beyond that process, not beyond imagination. Beyond verification, the difference matters. Human beings can imagine almost anything. Verification is far more restrictive. Science derives its strength from this restriction. Ideas must confront evidence. Hypotheses must survive observation. The event horizon interrupts that relationship. Beyond it, reality continues, yet evidence cannot return. The result is a curious situation. Physics can describe what should happen. Mathematics can predict consequences. Theories can be developed. But direct confirmation becomes impossible. The black hole becomes a natural experiment in epistemology, a test of what knowledge means when observation reaches its limits. This is one reason black holes occupy such a unique place in philosophy as well as science. They force questions that extend beyond astronomy. What qualifies as knowledge? What qualifies as explanation? What does it mean to understand something that cannot be directly observed? These questions become even more significant when viewed against the broader history of science. For centuries, scientific progress expanded access. New instruments revealed new layers of reality. Microscopes exposed hidden biological worlds. Telescopes exposed hidden cosmic worlds. Particle accelerators exposed hidden quantum worlds. Every technological advance seemed to push deeper. Reality became increasingly transparent. The trend appeared almost inevitable. Black holes interrupt that narrative, not because instruments are insufficient, because the universe itself imposes restrictions. The limitation becomes part of the phenomenon. No engineering breakthrough changes the horizon. No larger telescope bypasses it. No detector retrieves information that never arrives. The obstacle is woven into the structure of space-time, and this realization introduces a subtle shift in perspective. The question stops being what do we not know. The question becomes what can be known at all. These are not the same question. The first concerns information. The second concerns possibility. The first can often be solved, the second may not. This distinction has appeared elsewhere in science. Quantum mechanics already revealed limits. Certain pairs of properties cannot be simultaneously measured with arbitrary precision. Observation itself affects outcomes. Certainty possesses boundaries. Black holes extend this lesson, not into measurement alone, into access itself. Reality may contain regions forever beyond participation, forever beyond direct experience, forever beyond confirmation. The possibility feels uncomfortable because human curiosity evolved in a world where access usually exists. A mountain can be climbed, a river can be crossed, a forest can be explored. Physical obstacles eventually yield. The cosmos is not obligated to share that characteristic. Some horizons may remain permanent. Some perspectives may remain unavailable. Some truths may exist without any observer capable of verifying them. This idea has strange emotional consequences. For much of history, humanity imagined itself becoming progressively less isolated from reality. Knowledge would bridge the gap. Science would illuminate the unknown. The darkness would recede. Black holes suggest a more nuanced picture. Knowledge is but so does awareness of limitation. Every new discovery reveals additional boundaries. Every deeper layer exposes deeper uncertainty. Progress remains real, yet completeness retreats. The horizon moves. And perhaps nowhere is this more evident than in the concept of a theory of everything. The phrase carries a certain mythic quality, a final framework, a complete explanation, a unified description of Micah. The dream is understandable. Human beings seek coherence. We want the pieces to fit together. We want reality to make sense as a whole. Black holes quietly challenge that ambition. Not because unification is impossible, because even a perfect theory might not eliminate inaccessible regions. Explanation, application and observation are not identical. A theory may describe reality beautifully while leaving parts of reality forever beyond direct verification. The distinction is easy to overlook, yet it matters enormously. A map can represent territory without allowing access to every location. A theory can represent reality without making every aspect observable. Black holes remind us of this continuity. The horizon remains, the separation remains, the limitation remains, and once this principle is accepted, another possibility emerges. Perhaps human beings have consistently underestimated how partial every perspective truly is, not only in astronomy, everywhere. Every observer occupies a position. Every measurement occurs from somewhere. Every viewpoint excludes countless alternatives. Complete perspective may be more than difficult. It may be fundamentally unattainable. The observable universe itself demonstrates this. We can only see regions whose light has reached us. Beyond that lies more reality. Not hypothetical reality, actual reality, yet inaccessible. The horizon of the observable universe functions as another boundary of knowledge, different from a black hole horizon but conceptually related in both cases. Existence extends beyond observation. Reality exceeds perspective. The lesson repeats, again and again, and perhaps that repetition's meaningful. Perhaps black holes matter so deeply because they reveal a truth extending far beyond themselves. A truth about knowledge, a truth about observers, a truth about the relationship between understanding and reality. The truth that the universe may always be larger than any description we construct, not merely larger in size, larger in possibility, larger in complexity, larger in mystery. The realization is not necessarily pessimistic. It can even be strangely calming. If reality exceeds understanding, then uncertainty is not failure. It's a natural consequence of existing within a universe vastly larger than the minds attempting to comprehend it. Black holes become symbols of that condition, not symbols of ignorance. Symbols of perspective, markers reminding us that every observer stands within a limited horizon, that every explanation emerges from a particular vantage point, that reality itself may extend far beyond what any single framework can capture. And if that is true, then the most unsettling possibility is not that black holes hide information. It is that they reveal something about the nature of knowledge itself, something that becomes even more difficult to ignore when modern theories begin suggesting that the horizon, space-time, and perhaps even gravity may not be fundamental after all. There is a moment that arrives in many scientific revolutions, a moment when researchers stop asking whether a theory is incomplete and begin asking whether the theory's most basic assumptions are wrong, not slightly wrong, fundamentally wrong. The Earth was not merely misplaced within the cosmos. It was not the center at all. Time was not merely measured imperfectly. It was not universal. Matter was not merely composed of smaller pieces. The pieces themselves behaved according to rules no one had anticipated. Every major transformation in science begins with a similar realization. The framework that once seemed indispensable becomes provisional, useful, powerful, but incomplete. Black holes have gradually pushed modern physics toward another such moment, because after decades of effort, many of the deepest problems remain unresolved. The information paradox persists in various forms. Quantum gravity remains unfinished. The singularity remains unexplained. The event horizon remains conceptually unsettling. And when a problem survives this long, physicists begin exploring increasingly radical possibilities, not because they enjoy radical ideas, because conventional ideas stop working. One of the strangest developments to emerge from this search is the growing suspicion that space-time itself may not be fundamental. This possibility is difficult to absorb because space-time feels unavoidable. Everything happens somewhere. Everything happens sometime. Space and time seem less like features of reality and more like reality itself. Questioning them feels almost meaningless. Yet history repeatedly demonstrates that apparent foundations can conceal deeper layers. Temperature once appeared fundamental. It emerged from molecular motion. Solidity once appeared fundamental. It emerged from atomic interactions. Perhaps space-time belongs to the same category. Perhaps it is not the foundation. Perhaps it is a consequence. This possibility first appeared almost absurd. Yet black holes kept pointing in that direction. Again and again, attempts to understand horizons, entropy, and information revealed unexpected relationships. Information seemed increasingly important, sometimes disturbingly important. The equations suggested that the amount of information associated with a black hole scales not with its volume, but with the area of its horizon. The result was surprising. Human intuition associates information with contents, with what exists inside something, yet black holes appeared to care about surfaces, boundaries, edges. The implication was subtle but profound. Perhaps the horizon contains more significance than anyone initially realized. Perhaps the boundary is not merely a boundary. Perhaps it is part of the explanation itself. From these ideas emerged one of the most remarkable concepts in theoretical physics, the holographic principle. The idea sounds almost mystical when first encountered, yet its origins are mathematical. If information describing a region of space can be encoded on a lower dimensional boundary, then the relationship between volume and reality becomes less obvious. Three-dimensional experience may not be fundamental. Depth itself may emerge from more primitive structures. To understand why this is unsettling, imagine discovering that every landscape, every star, every galaxy, and every moment of your life arises from information organized on a distant boundary. The world would remain real. The mountains would remain solid. The stars would continue shining. Nothing observable would necessarily change. Yet the conceptual foundation would transform. Would transform completely. Reality would become stranger than appearances suggest. This possibility remains theoretical. Yet the mathematics supporting holographic ideas has produced remarkable insights. Enough insights that many physicists take the concept seriously. And once again, black holes stand at the center. Not because they provide proof, because they provide clues. The horizon continues behaving like something more than a simple boundary. Information continues behaving like something more than a bookkeeping tool. The deeper researchers investigate, the more reality begins resembling a network of relationships rather than a collection of objects. And then matters become stranger still. Because some modern approaches suggest that space-time itself may emerge from quantum entanglement. Entanglement is already one of the most counterintuitive features of quantum mechanics. Two systems become correlated in ways that defy classical expectations. Separate objects behave as parts of a larger whole. The implications remain subtle and often misunderstood. Yet within certain theoretical frameworks, entanglement appears capable of generating geometric structure. Space itself may emerge from informational connections. The idea sounds extraordinary, yet it continues appearing in serious research. If correct, the consequences are difficult to overstate, because it would mean that the stage upon which reality unfolds is not fundamental. The stage itself emerges, space becomes a consequence, geometry becomes a consequence, perhaps even gravity becomes a consequence. The universe begins to resemble something built from deeper principles hidden beneath ordinary perception, and black holes remain among the strongest clues that such principles exist. The event horizon occupies a particularly important role in these discussions. For generations, physicists treated the horizon as a relatively straightforward concept, a boundary, a point of no return. Yet modern debates have complicated the picture dramatically. Some proposals suggest that horizons may possess unexpected quantum structure. Others suggest that our understanding of what happens near the horizon remains incomplete. One especially controversial idea became known as the firewall hypothesis. The proposal emerged from attempts to resolve conflicts between quantum mechanics and relativity. According to classical expectations, an observer crossing the horizon should experience nothing unusual locally. The transition should be smooth, yet certain quantum arguments suggested that preserving information might require something much more dramatic, a region of intense energy, a kind of destructive boundary, a firewall. The proposal remains highly debated. Many physicists reject it. Others view it as evidence that deeper principles remain hidden. The details are complex. The significance is simpler. Even the nature of the horizon itself remains uncertain. A feature once considered well understood has become the subject of renewed controversy. The closer science approaches certainty, the more ambiguity appears. This recurring pattern reveals something important. Black holes are no longer merely testing existing theories. They are actively reshaping them. Every major attempt to resolve their paradoxes generates new ideas about reality, new frameworks, new possibilities, new questions. And beneath all these developments lies a growing suspicion. The suspicion that gravity, space-time, horizons, and perhaps even physical existence may emerge from something more fundamental than anything currently included in ordinary intuition. The consequences extend far beyond black holes, because if space-time emerges, then location is not fundamental. If gravity emerges, then attraction is not fundamental. If horizons encode information, then geometry is not fundamental. Layer after layer of apparent certainty begins dissolving. What remains becomes increasingly abstract, increasingly relational, increasingly difficult to visualize. And this is where the emotional character of the mystery reaches its peak. The original question seemed straightforward. What is a black hole? Over time, the question expanded. What happens to information? What is space-time? What is gravity? What is observation? What is reality? The subject has grown so large that the black hole itself almost disappears. The object becomes secondary. The implications become primary. This transformation carries a strange irony. Black holes entered science as extreme astrophysical objects, dense remnants of gravitational collapse. Yet after decades of investigation, they increasingly resemble windows, not into distant regions of space, into deeper layers of existence. Windows through which the limitations of current understanding become visible. Windows revealing that the universe may be built upon principles radically different from those suggested by everyday experience. And if that possibility is true, then an unsettling conclusion follows. The event horizon may not be the ultimate boundary. The singularity may not be the ultimate mystery. Even space-time itself may not be the deepest layer of reality. The true mystery may lie beneath all of them, a hidden foundation from which gravity, geometry, information, and existence emerge. A foundation humanity has not yet learned how to see, and if such a foundation exists, then black holes are not merely strange objects scattered throughout the cosmos. They are signposts pointing toward it, silent markers indicating that reality is far stranger than the universe we currently imagine. After travelling this far into the subject, something unusual begins to happen. The urgency fades, not because the mystery has been dissolved, because it has expanded beyond resolution. The black hole that first appeared as a dark object in space has become something else entirely. A question, a boundary, a mirror, a reminder. And perhaps this transformation tells us something important. Human beings often approach mysteries with the expectation that answers will shrink them. That uncertainty will gradually retreat. That investigation will convert the unknown into the known. Sometimes this happens. A puzzle is solved. A mechanism is revealed. The darkness recedes. Yet there are other cases in which investigation produces the opposite effect. The mystery grows, not because understanding fails, because understanding reveals deeper layers beneath it. Black holes belong to that category. The more carefully scientists study them, the larger the questions become. The object itself remains astonishing, a region where gravity overwhelms escape, a horizon dividing accessible reality from inaccessible reality, a consequence of collapsed space-time. Any one of these features would be extraordinary, yet none of them now seem like the central issue. The deeper issue is what black holes have revealed about the limits of explanation. Again and again, they have exposed hidden assumptions. Assumptions about space, assumptions about time, assumptions about information, assumptions about observation, assumptions about what it means to know something at all. The process has been strangely humbling. For centuries, humanity's scientific story often appeared directional. Each generation inherited a larger and more accurate picture of reality. Mistakes were corrected. Knowledge accumulated. The universe became clearer. Black holes have not reversed that process. They have complicated it. Knowledge continued to expand, yet so does awareness of uncertainty. Every solution uncovers new question. Every deeper explanation exposes new foundations requiring explanation themselves. The horizon recedes. The map grows. Completion remains distant, perhaps infinitely distant. This realization can feel unsettling at first. Human beings prefer closure, narratives with endings, questions with answers. The mind seeks stability, a final framework, a place where inquiry can stop. The universe offers little evidence that such a place exists. Instead, reality seems layered, each level emerging from deeper levels, each explanation resting upon deeper principles, each discovery revealing larger contexts. Black holes simply make this structure impossible to ignore. They force us to confront the possibility that understanding may be an endless process rather than a destination. And there is something strangely beautiful about that, because uncertainty is often mistaken for weakness. Science is sometimes portrayed as a machine for producing certainty, a mechanism that converts mystery into facts. The reality is subtler. Science succeeds not because it eliminates uncertainty. It succeeds because it learns how to navigate uncertainty honestly. Black holes demonstrate this remarkably well. Physicists openly acknowledge what remains unresolved. The information paradox, quantum gravity, the nature of space-time, the reality of singularities. These are not failures. They are frontiers, places where knowledge has reached its current edge, and edges are valuable. Without edges, exploration cannot exist. Without unanswered question, discovery loses meaning. The black hole therefore becomes something more than a scientific problem. It becomes a symbol of intellectual humility, a reminder that reality is not obligated to match expectation, a reminder that nature remains larger than every framework used to describe it. And perhaps that lesson extends beyond physics. Human beings occupy a very small region of space and time, a narrow band of experience, a brief interval between birth and death. Yet from within that narrow interval, we attempt to understand a universe nearly 14 billion years old, a universe spanning distances so immense that light itself struggles to cross them, a universe containing structures larger than imagination and processes lasting longer than civilizations. The ambition is extraordinary. The success is extraordinary. The limitations are inevitable. Black holes reveal those limitations clearly because they sit at the edge of what current understanding can comfortably explain. They are not the only such boundary, but they are among the most visible, among the most dramatic, among the most philosophically revealing. The darkness at their centers becomes almost symbolic, not a darkness of ignorance alone, a darkness of scale, a darkness created by the difference between finite minds and an apparently inexhaustible reality. And perhaps this is why black holes continue exerting such fascination. Not because they threaten us. In practical terms, they rarely do. Not because they are monstrous. The universe is indifferent to human categories of fear. Black holes fascinate because they expose perspective. They reveal how small the familiar world truly is, how local human intuition truly is, how provisional our explanations may be. And yet they also reveal something else, something quieter, something easy to overlook. The fact that finite beings can recognize their own limitations at all. The fact that a species living on a small planet around an ordinary star can detect horizons 26,000 light-years away, can measure gravitational waves from merging black holes, can infer invisible structures shaping distant galaxies, can discover boundaries in knowledge itself. There is something remarkable in that achievement. Not because it conquers mystery, because it encounters mystery consciously. The universe may remain larger than understanding, yet understanding continues reaching outward, patiently, gradually, across generations. Black holes do not diminish that effort, they give it meaning, because a mystery that can never be fully exhausted becomes a companion rather than an obstacle, a horizon toward which inquiry moves without expectation of final arrival. And as the cosmic scales continue expanding, as theories evolve, as new observations arrive, one possibility remains quietly present, the possibility that the deepest truths about black holes are still waiting beyond the current horizon. Not hidden because nature is deceptive, hidden because reality is deeper than the frameworks we've inherited. The darkness remains, not as an enemy, not as a void, but as a reminder that every answer exists within a larger mystery, and that the universe may be far stranger than even our most ambitious theories currently allow. In the end, the most unsettling possibility is not that we were wrong about black holes. Science has been wrong before. Entire models of reality have been revised. Worldviews have collapsed. new phénomènes have emerged. Correction is not a weakness of science. It is one of its defining strengths. The deeper possibility is something quieter, something harder to resolve. The possibility that black holes are showing us what it feels like to reach the edge of a way of thinking. For centuries, humanity has expanded its picture of existence. The Earth became a planet, the Sun became a star, the Milky Way became one galaxy among countless others. Space expanded, time expanded, reality expanded. At every stage, the universe grew larger than expected, and at every stage, human intuition became less reliable. Black holes may represent another step in that process, not because they are the largest objects, not because they are the most powerful, but because they force us to confront the limits of the concepts we use to understand anything at all. Space, time, information, observation, cause, effect, reality. The closer we move toward the horizon, the less secure those concepts appear, and perhaps that is the true significance of the darkness. Not that it hides answers, but that it reveals the boundaries of the questions themselves. Somewhere in the distant universe, stars continue orbiting invisible centers. Galaxies continue evolving around supermassive black holes. Gravitational waves continue crossing intergalactic space. Light continues traveling through expanding cosmic darkness. The universe goes on. Silent, immense, indifferent, whether human beings understand it or not. And yet understanding continues. Observatories will gather new data. Theories will be refined. Old assumptions will be challenged. Future generations may discover principles that today remain unimaginable. Perhaps the information paradox will be resolved. Perhaps quantum gravity will emerge. Perhaps space-time itself will be understood in ways that currently seem impossible. Or perhaps every solution will uncover deeper mysteries beyond it. History suggests that reality often prefers the sky outcome. The horizon moves, the map expands, the unknown remains. And so the black hole endures as more than an astronomical object. It endures as a perspective, a reminder that existence is larger than familiarity, older than memory, stranger than intuition. The darkness at its center may conceal new physics, or deeper geometry, or informational structures not yet understood. But regardless of what future discoveries reveal, one lesson already seems clear. The universe is under no obligation to resemble the world that human minds expect. It never has. Perhaps it never will. And maybe that is why black holes continue drawing our attention. Not because they are places where knowledge ends, but because they are places where humility begins, where certainty softens, where perspective widens, where the immense age and scale of reality become briefly visible. Tonight, somewhere beyond sight, countless black holes remain hidden among the stars. Silent centers, invisible architects, dark regions wrapped in deeper darkness. Exist. We know some of what they do, and yet their deepest nature remains unresolved. A small pocket of uncertainty suspended inside a universe already vast beyond comprehension. The night sky looks unchanged because of that uncertainty. The stars still shine. The galaxies still drift. But the picture feels different, a little larger. Larger, a little stranger, a little less complete. And perhaps that incompleteness is not something to fear. Perhaps it is simply the shape of reality itself. A reality whose horizons always recede faster than understanding can follow. A reality that remains, even now, waiting beyond the edge of what we think we know.